Okay. So we were right about here, right? And we had talked through the reflection part of that, I know, and the transformation part of it, right? That's how we got that point. And we had decided that we know that this means that we are going to reflect in the y-axis. So instead of looking like this, it's going to be pointing the other way. And then this moved us to the right too, because x is a liar. And then this too does a horizontal compression, but we don't even really need to worry about that. If we've got that, we know the general shape in which direction it goes, but it would be nice to have one other point. So let's find the y-intercept, and the y-intercept happens when x is what? 0. So if I put a 0 in here, I'm going to get the square root of 4, which is 2. So my y-intercept is at 0, 2, and then that's basically what my graph looks like. Okay. We agree with that? So my domain, left to right, right? I start way out here. My x values start at negative infinity. That's always a parenthesis. And I go until I hit 2. Do I include 2? Yes, because 2 is an x value that I graph on my function. Then my range, oops, this is, I start, what's the first y value I get to? 0. Do I include it? Yes. And then I go all the way to what? Positive infinity. Writing infinity to 0 is wrong and makes no sense. Left to right, bottom to top, least to greatest every single time, okay? And we're going to write tons of intervals on tons of things, and I promise you this is the one that's going to make the most sense overall, okay? All right, so let's look at D. Now, the equation, so I do expect that on A and C, you know what the parent functions look like. On B, that you know it's irrational and can figure out some asymptotes, that kind of stuff. On D, I don't expect you to, and I don't expect you to know what B looks like before we start. We talked about that. On D, I don't expect you to know what it looks like. You've probably never graphed this, maybe never even seen it, but that doesn't mean that there's absolutely nothing you could do. Because if that was x squared plus y squared, that would be the equation of a circle. Radius would be 2, centered at the origin, but it's not a plus, so it's not. But I could get some intercepts here, right? So to find the x-intercept, what has to be true? What has to be true about y? 0. So if I make y 0, that will give me x squared equals 4. Then I take the square root of both sides, and x equals what? What? Plus or minus, yes. Plus or minus 2. You cannot forget that. Some of you will miss that plus or minus every single time it happens. Don't be that person. Tell yourself, I'm not going to be that person. Okay? Because you'll end up in math jail. See? I introduced a square root and didn't use plus or minus. That's bad. You don't want to end up there. Okay? So plus or minus 2, which means that I know that when y is 0, x could be negative 2 and x could, it is positive 2 and is negative 2. So then my y-intercept happens when? When x is 0. So when x is 0, that gives me negative y squared equals 4. So that means that y squared equals negative 4. So what does y equal? What's the first thing I write? Plus or minus, and then what's the square root of negative 4? We do with 2i, very good. So is that something that I can graph on my function? No, because it's imaginary. That means I don't have any y-intercepts. And that's the extent of what you would know how to do on this, because to get the rest of this graph and know exactly what it would look like, there's a whole lot of other stuff you have to do. And this is something that you don't do much in any course anymore. So we're just going to sketch the rest of it and go with it. It looks like this, basically. It's called a hyperbola. It's a conic section. They have some applications in the real world, but not a ton, and it doesn't really connect to any other math, and that's why it's kind of been taken out of the curriculum for actually knowing how to graph purposes. All right, so, because all we really care about here, right, is getting the domain and range. So my domain, I start where? Way out here at negative infinity, never include it. I go until I get to negative 2. Do I include that? Yes, because that is an x value that's plotted on my graph. And then I got to start over, so what do I have to write next? The u, okay? The union c, it's technically not a u, but yeah. And then 2. Yes, do I include the 2? Yes, and then I go until I get to infinity, and that's my domain. And that's way better than trying to figure out which way your little things are pointing and where the x goes and what your inequalities look like, because that would just be a hot mess for some people, I know. All right, so then range. What's the smallest? Where do I start with y? Negative infinity, and I go all the way to positive infinity. Any questions about any of those? All right, so like I said, we're going to be writing intervals for a lot of other things. The only intervals that we are going to write that include the y values are range. That's it. Everything else we do are intervals of the domain, and that's important for you to know because we're going to be talking a lot about y, but we write about x. And I understand how sometimes you end up writing the y's down, so you have to remind yourself, I'm talking about y, I'm writing about x. And I will remind you of that often, but that's what's happening, okay? So let's look at, so flip it over. And yes, it's upside down. I had somebody ask me about that yesterday. There's a reason for it. It'll make more sense at the end of class. All right, so we're going to talk about and write about graphical behavior of functions. Things that you maybe have talked about before. I don't know, well, at least increasing and decreasing probably. I don't know how much you really wrote the intervals. But so if my function is increasing, right, so if I'm increasing, the input values increase, the output values always increase. So that means we are always going on the x-axis for our domain from left to right, just like we read. So as x gets bigger, because I'm going from left to right, as x gets bigger here, my y values also get bigger, right? So that means that this is increasing. From negative infinity to infinity, this is increasing. I don't care what y values are happening, is it getting bigger? That's all I really care about. If it's decreasing, as the input values increase, meaning I'm still going left to right, the output values always decrease. So my y values are getting smaller. Okay? Increasing and decreasing makes sense? If the function is increasing or decreasing, that means what are the function values, and the function values are your y values. All right? Now, these are lines. When you have talked, well, actually, let me back up and ask you another question first. When we talk about concave up and concave down, it said we're going to be talking about the rate of change. What is another word or another way to say rate of change? The slope, exactly. The slope. Somebody last period also said ratio. It is a ratio. That's how we get the slope, right? It's the ratio of the change in the y over the change in x. So we're looking at not the function values, but the slope of the function. Now, the only slopes you have really talked about up until now are slopes of linear functions. And these are constant slopes. So if my equation is y equals 3x plus 7, my slope is 3, and it's always 3. That's why you can pick any 2 points, doesn't matter which ones, and you're going to get the same slope, right? We could all pick different points on this line. We find the slope, we do it correctly, we all get the same answer because the slope doesn't change. Well, here on curves, your rate of change changes, and how it changes tells you a lot about the function. So when we're looking for concave up, your rate of change is increasing. So what we really want is the rate of change at a single point. The problem is we can't find that unless we have some calculus knowledge, which this isn't a calculus class, right? But we can estimate it by getting really, really close by picking 2 points super close to each other, finding that, finding that slope, and then that would be pretty darn close. Does that make sense to you? So when we want that just 1 point, what we would actually want is the line tangent to the function. That should sound familiar to you from geometry. When you found, y'all talked about circles and tangent lines, that tangent line intersected at exactly 1 point. You remember that? You also did secant lines, which intersected at 2 points. We only know how to find the slope using 2 points. That means that we would have to use the secant lines to estimate it, but if we can get those 2 points really, really close to each other, it'll be a good estimation for the tangent line. Make sense? So when we talk about them and when we write, you know, kind of sketch them, we'll probably sketch some tangent lines or think about the tangent lines, knowing that that's not really what we can find. But if we're talking about the slope of this function at any given point would be the slope of that tangent line. So all these little lines that you could draw, like these little line segments. So I could draw these little line segments. These are not coming out well. I got to stand in front of it. I'm trying not to stand in front of it. Right on the outside so we can pretend like it's just touching at one point or two really close points. And I'm not really just trying to sketch the curve. I'm trying to make little line segments. You can also use your pencil to think about it, right? So it says the rate of change is increasing. So this slope right here is negative, right? And it would be like, I don't know, a -2 or whatever it is. And then as I go down here, my slope is still negative, but do you see how it's getting closer and closer to 0? And then I hit my 0 slope, and then my slope gets bigger and bigger and bigger. So the entire time here, my slope is increasing, right? So even though here the function is decreasing, this is decreasing at an increasing rate. So it's decreasing, but the slope is increasing. See the two different things? So we're going to be looking at what's happening with the function and what's happening with the slope. And you can be asked those questions back and forth, so you have to remind yourself, now I'm talking about the function, now I'm talking about the slope, because it's easy to not really get them mixed up, but think about the wrong one because you're not focused on which one you're looking at. And then if it's concave down, the rate of change is decreasing. So again, if we drew our little line segments, or then we could just really use our pencil. Those don't even look like line segments, but you get it. So here is my positive slope, right? It's pretty steep. Then my slope gets less and less steep until I get to 0. And then it's a negative slope, but just a little bit, but then it gets more and more negative. So here, my slope is decreasing the entire time. Function is increasing right here, but the slope is decreasing. Two different things going on. Okay? We good with that so far? All right. So the increasing, decreasing may not really be new, and if it is, it doesn't really bend your brain too much. I understand that you haven't really talked about changing slope, slopes that change along the way before. Concave up and concave down graphically, most of the time, look pretty much like going up and going down, okay? But sometimes they don't, and sometimes we don't have the graph. That's why we also need to think about what's happening with the rate of change. Okay? And because of that, we're going to have a little fun chart, right? So in calculus, you have a fun box. Here we're going to have a fun chart because it's a little bit of the fun box. And this is going to help you. It's going to be one of those things that, depending on how the question is asked, might be something that you need to rewrite every time a question comes up, because we do that in calculus a lot. Rewrite the fun box. I do too. Just rewrite it so we can get it out there. Okay, so we have an f. That's for the function. Okay. And then we have concave up and concave down. So it kind of looks like fun, but it's not really a u and an n. We're representing concave up and concave down. And then increasing and decreasing. And I can see some of y'all are not listening to anything I'm saying, and you're answering all these questions, and you're probably going to be really sorry about that, because then you're going to be confused on other things, because it's not all about answering the next question. I promise you that. So that's the first line. And then we're going to have slope. Okay, that kind of goes under the F. And then since I went up and down, I start back over up and down, and then this is a plus and a minus, and I'll tell you what all this means. Okay. So F represents my function. When my function is concave up, my slope is increasing. When it's concave down, my slope is decreasing. If my slope is positive, then my function's increasing. If my slope is negative, then my function's decreasing. You have to understand it both ways. It's not all about looking at a picture and being able to write an interval down. We're going to have to look at it from a table, from an equation, all those different types of things. So if you don't understand it holistically and like this as well, it's not all about just looking at a graph, okay? So the other thing is this. You remember, and you don't have to draw this part, but we talked about, so I'm going to erase this in a minute, but we had the cubic, right? And I asked you what this was right here, and that's our point of inflection, yes? So it's a point of inflection because on your cubic, and you probably never, I know you didn't talk about it this way, this function is concave down right here, and then it's concave up. That point of inflection is where you change concavity, either concave up to concave down or vice versa. So right here, in your little a little chart, which isn't necessarily something you would have to write every time you write the chart, but we're going to do this right here. This right here is your point of inflection. And we'll talk more about points of inflection in future lessons, and we'll talk more about this fun chart. I was really planning on talking about this in another lesson, but then as I was doing this today, I was like, no, we really need to start it now. So it goes right here, which means point of inflection happens when I change from concave up to concave down or vice versa, but that's also happening when the slope changes from increasing to decreasing, okay? And then this just can kind of help you to refer back to this. Sometimes it's easiest to look at the graph. Sometimes it's easiest to think about this. It kind of depends on what's happening with what you're doing, okay? We good with that? All right. So let's see. Let's look at example 4. A couple of things I want to talk about in the wording, okay? Wording is important here. This talks about the graph of h of x. It says the graph of h of x is shown above. Use the graph of h to find the open intervals where h has the following behaviors. This is also probably the first time you have seen a function referred to without the of x part of it, right? Anytime you see f of x, it's always like f of x, f of x, f of x. We talk about the function. But it is appropriate to drop the x parenthesis part and just call it h. That also, because it tells me this is the graph of h, I could have the graph of h. I could have the graph of the slope of h, okay, because we'll get into some of those. So one thing we want to get in the habit of doing is whatever this is the graph of, I'm going to label it. This is the graph of h, not of the slope of h. That way, when it's asking me different things, I'm not getting mixed up with that, okay? Which shouldn't happen today on these questions, but again, we're just going to get in the habit of that's h. Sometimes in calculus, we write it like 3 times around so we don't mess it up, because you can look at it and be thinking something different. All right, let's look at A. So it says h is increasing. So I want the intervals when h is increasing. Well, it's decreasing here, right, because we're talking about the y values. Then it's increasing from here to here. So my y values increase from 1 to 3. The 1 and the 3 mean nothing because we are talking about y. Y increases. We write about x. So it is increasing on the interval from -2 to 0. You see what I mean about talking about y and writing about x? What the difference is there? Okay. Is that the only place it's increasing? No. So then we start decreasing, right? Something weird happens here, but I'm still decreasing. And then I start increasing here, which goes from 4 to 7. What do I need first? Union, and then 4 to 7. And these are always open, okay? I'm telling you they're always open. If you sat in on a training for teachers for calculus, you would hear teachers arguing about why it should and shouldn't be. And it's been an argument for years, and nobody's ever going to win. So it's possible that some people would have them closed. But here it literally says open intervals. But let me explain to you why we don't do that. First of all, when this is increasing till we get to here, then it starts decreasing. So at 0, is it increasing or decreasing? Can't be both, right? And so but which one is it? We don't know, so we just leave them open. And even if you felt strongly the other way, I suggest, well, I'm only going to count it right this way, because if we do this, there are other times where it absolutely has to be open, especially when we're talking about positive and negative. And this way, the only time you have to worry about open and closed is domain. The only time you have to worry about writing y values or using open closed is with domain. Wait, I said that wrong. Back up. The only time you have to worry about writing y values is with range, is what I meant to say. I don't know if that's what came out of my mouth. And then the only time you have to worry about open and closed is if it's domain and range. Okay? Everything else, just open intervals, and there won't be any question about it. Okay? Consistency is the key here. All right. So then we need to look at h decreasing. So I think it's decreasing here, would you say, and then here. Do we agree with that? So h is decreasing from -4 to what? -2. And then from 0. And then something happens here, and it's not actually a point of inflection because this is a piecewise function. It's not a continuous function, but I mean, it's continuous, but it's piecewise. It's a different thing. But either way, but it's decreasing the whole time. So from 0 to 4. All right, so now let me ask you about this section right here. This section right here, do you think this is concave up or concave down? Now, we know it's decreasing because we just put it there. But how do you know, not by looking at the graph, but from our fun chart over there, what has to be true for a function to be concave up? What has to be true about the slope? Has to increase. And if it's concave down, the slope is decreasing, right? What is happening to this slope right here? It's staying the same, right? It's linear, so the slope is constant, right? The slope doesn't change. It doesn't increase or decrease. So this right here can't be concave up or concave down because it's linear. Make sense? You can only be concave up or concave down if you're a curve. If it's linear, it's none of the above. We good on that? And it's because the slope is constant, not increasing or decreasing. Now, the function is decreasing, so maybe you want to think it's concave down. Even if it looked like this, it's still not concave down anywhere because it's linear. Okay, we good with that? All right, so we only really worry about the curvy parts. All right, so concave up. What are we thinking about concave up? Where does it start? You're not sure? You're not sure, that's fine. Let's do concave. Well, let's just talk about concave down. Where does concave down start? -2, we agree with that. Then we got to figure out where it stops. Is it still concave down here? So remember, concave down means my slope is decreasing. So I have a really high positive slope, and then it becomes 0, and then it becomes negative, and then it gets really, really steep, and then look, it starts to get bigger again, right? So right here, where it's not a point of inflection because it's a weird kind of graph, but that is where it changes from concave up to concave down, because that's where my slopes change from decreasing to increasing. Does that make sense to you? That's why I like just taking your pencil or whatever and thinking, okay, this is what's happening with my function here. That's why this is important. So that means we start at 2 and we go to where? 7. Very good. All right, we good with that? So if it's concave up from here to here, it's neither from here to here. That means concave down has to be from here to here. We agree with that. This asks for h being both increasing and concave down. So where does that start? -2, because this is increasing, not my slope, right? My slope isn't increasing, but my function is increasing. So it's increasing at a decreasing rate is what's happening. And that's when the words can get kind of weird. So that's why it's better to kind of think of concave down, but increasing goes from -2 to 0. And that will not get as confusing in your brain once we do it more and more, I promise. Because it is something new that you're thinking about. All right, so then h is both decreasing and concave up. So we knew it was concave up from right here. Where does the decreasing part start? At 2 and goes to what? 4. Any questions at all? Anything I need to repeat? Please do not be afraid to speak up. And right now, it may just be soaking in your brain and you don't really have a question yet because it's still like, what? And then if it happens, later on or Monday when you come back and say, re-explain this, it's all good, okay? We good with that? All right, so we're going to skip example 5, and I'm going to give you something else. We're going to do a couple together, and then I want you to have some time to talk with each other. We'll get that put in your ISN in just a minute. Here, I think that's 5. That might be extra. So go ahead and put your name on it. That might be an extra one. If so, you can just leave it on the table. All right, so this is a little 2 truths and a lie activity. Oh, the extra one. Start with number 1. Let's look at that one first. Okay. So there's 3 statements on each one of these. We're going to identify which of the 3 statements is false and explain why it's false or correct the statement, one of the 2. All right, so let's look at this first one. It says the graph of f of x, and it's already labeled for me, so that's good. The graph of f of x is increasing on the interval from 3 to 6. And I encourage you to write on the graph, literally trace it out on stuff, 3 to 6. Do you think it's increasing there? Yes. What is increasing? Is it the slope that's increasing? What is it? When it says increasing, what is it asking you about increasing here? Is it asking you if the slope is increasing? No, it's asking you if the function value, which means y, that's what we're looking at for increasing there, right? So again, we'll make sure we separate those. So we say this is true. All right, so then the graph of f of x is concave up on the interval from 3 to 6. What do you think about that? True. It looks like it, plus if I put my pencil here, I'm at 0, and then it gets bigger and bigger and bigger, so that's a true right there. Okay, which probably means 3 is false, but if we think it's true, we have to reevaluate everything. It's concave down on the interval from -1 to 3. So from -1 to 3 is right there. Because when it gives me the interval, we're talking, these are intervals of the domain. That's why that's the part here. I don't care about the y values. What do you think about that? Is it concave down? No. It's concave what? Up. And is it increasing or decreasing? Decreasing. Okay. So when we explain ourselves here, we can say f. You can say f of x if you want, but I'm just going to show you all you have to say is f. F is decreasing, but I'm going to abbreviate. DEC. Totally fine. We have to write stuff, but we can abbreviate some things we don't. I'll make sure I kind of help you with what's what so we're not writing forever. F is decreasing and concave, we're not going to abbreviate that because that could be some other things. Concave up on -1 to 3. So we don't even have to say on the interval. On -1 to 3, that implies the interval. That's totally fine. But all those words there at least have to be there. We good with that? And you'll get better with that too. Especially if I understand that at the beginning, when you're on your own and you're explaining things and you may not be fully comfortable with the words, but I need you to write down whatever you think is right because I can't help you fix what's coming out of your brain if I don't see at least what you think it should be. You with me on that? So write it down, even if you're like, I think this is a hot mess, but I'm trying to get my thoughts down here and I can help you fix that. But if you give me blanks, I don't know how to fix that. I can't help you. And you're not all going to have the same issues with how to word things, okay? All right, let's look at number 2. The graph of g of x, and it's labeled for me, that's good, is increasing on the interval from 3 to 6. Okay, so do I go look at 3 on the y-axis? No. I go to 3 on the x-axis to 6, so this right here. All right, is it increasing on that interval, do you think? I think so, because when I say it, I mean g of x, which is the y values, they are increasing. That is true. All right, so then the graph of g of x is decreasing from 0 to 1. What do you think of that? Is that decreasing? Yes. Good. Now, it's not always the third one that's going to be false. It's just what's happening here. The graph of g of x is concave down from -4 to -3. So what do you think about that? False. It is concave up, and is it increasing or decreasing? Decreasing. So I'm going to say G is concave up and decreasing on -4 to -3. And so on the first one, I said decreasing first. On this one, I said concave first. It doesn't matter as long as you say them both. The order means absolutely nothing. We good? Any questions? All right, so then I want you to jump to, we're going to go to 5. So flip the paper over. So here we're talking, our graph is called K. The graph of K of x has a 0 at x equals 2. What does it mean when a function has a 0? X-intercept. So your zeros, your roots, your solutions, your x-intercepts, those are all the same thing with different names, okay? So x-intercept means I have something, you know, a function value on the x-axis. So do I have a 0 at x equals 2? And this is the kind of graph that you may not be 100% familiar with, but think about what you do know about these things. I'm not going to ask you what the equation is or anything like that. When x equals 2, is the y value 0? Yes. Okay, because when x equals 2, there's a hole here, right? It's like they took this point out and put it right there. So even though it doesn't cross the x-axis, that's why we can't even think about it as crossing the x-axis. I have a 0 at x equals 2 because when x equals 2, my y value is 0 because that point fell off or something. Okay, you with me on that? So this is true. You're going to be looking at a whole lot more interesting graphs than you have before, I promise. The graph of K of x has a 0 at x equals 3. What do you think about that? False, okay? Because that's where it crosses the x-axis, but there's not, when x equals 3, y does not equal 0, so this is false. Let's talk about this one, then we'll come back and write our statement. The graph of K of x has a 0 at x equals 5. What do you think? True. And that's the 0 you feel more comfortable with, right? So this is true. Okay, so let's go back up to our false and say something here. So I could say, instead, I'll say at, there's a few different ways we could say this, but at x equals 3, K of x equals what? -2. Very good. That point fell out too. Everybody good? All right, so I'm sorry, but flip back over because I meant to ask you another question, and I'm afraid if I wait until we finish that other one, I'm going to forget. Because it wasn't a question that was on there, but I wanted to talk about the graph, and it just occurred to me I didn't do it. Okay, so looking back at problem 2. We know that we said that on the interval from 3 to 6, it's increasing, which is totally true. On this interval, is it concave up, concave down, or both? Both. Because it's increasing the entire time, right? But what happens is our slopes are increasing, and then they start to decrease, right? So we're changing from concave up to concave down because in here we have a point of inflection, right? So it doesn't mean that it's doing the same thing the whole time. I just wanted to make sure we touched on that. All right, go back to number 6 now. Okie dokie. So graph of P of, so this one's called P of x, it's labeled for me. Says it's concave down when P of x is less than 0. So what does P of x less than 0, what does that mean? What is less than 0? Y. Okay, P of x, just like f of x, remember f of x means y. Your function, the function values are less than 0. Those are always your y values. So this is less than 0 here and here. Okay? So we've got to make sure we know. If we don't know what it means, we can't answer the question, right? So we know that that's what it means to be less than 0. Is it concave down there? Yes, that is true, because it's concave down here, because my slopes are decreasing the whole time. Okay. True, sorry. Then the graph of P of x is decreasing when x is greater than 0. All right, so when x is greater than 0, this is when x is greater than 0, right? And is it decreasing the whole time when x is greater than 0? What do you think? True. Decreasing the whole time. Now we have a point of inflection right here, right? So it's decreasing, and then it kind of slips in the rate, though. So it's decreasing the whole time, but the rate slows down, and then the rate speeds back up type of thing. Okay, so this is true. And then the graph of p of x is increasing and concave down where x is less than 0. So this is x is less than 0. Is it increasing the whole time? Yes. Is it concave down the whole time? No, it's false. So it's not both. So we can say P is increasing and concave down on, and since it says x is less than 0, there's no arrow on this, but there's also not a point at the end, so this kind of implies it goes to infinity, right? So I would say that it's from negative infinity to what? Where does it stop being? Concave down. Negative 2? Increasing to there, yeah. Negative 2. Okay, everybody okay with that? Any questions? All right, so let's talk about, I wanted you to have some time to do some of these with each other, but we don't really have that time today. So, but we're going to get this in our IS